Hello, ladies and gents. Let's get on with your probably the final video I'm going to do for this for you guys now. Well done on your mocks. Like seriously, if you're all getting like fours and above and things like that, you're in the top 50% of people in your age group this year. Over the top 50%. So even if you think you're not happy with the score that you got, you're doing really, really good. Okay. Let's have a look at question one then. We're looking at fractional distillation. First question, a suitable temperature for the furnace. The answer is then between 400 and 500 degrees Celsius, because if you look down here at the bitumen, 400 to 450 is its boiling point. 1.2, the correct answer here is looking at the separation by the boiling points. So we're looking at saying that the diesel here has got a boiling point which is below heavy fuel oil, which is 320 to 400, and it's above 180 to 260. If you're getting it wrong, people are getting it wrong because maybe they've got those the wrong way round. Alternatively, some people were talking about the length of the chains or the density, which didn't actually answer the actual point here. It's the separation on their boiling point. Two reasons why bitumen's not used as a fuel. A lot of people getting this and saying it's because it's too viscous and it's got too high a boiling point. And again, if we're getting it wrong, it's because people are putting in this idea that you need energy to make a fuel burn. Burning's exothermic, it gives out energy once you get it going. So it's this first bit that it's not very flammable, it's too viscous, its boiling point's too high. The reason the boiling point comes into it is because fuels are burning when they're turned into a gas. The liquid doesn't burn, wood doesn't burn as a solid. As it gets hot, gases start coming out of it and they burn. Okay. On question 1.4, most people are getting this right simply because we're looking at an alkane, so it's CnH2n plus 2. There's only one that doesn't fit the pattern. The rest of them all have the same pattern where the H is twice the C. On 1.5, most people from our lot are getting that a high temperature is needed. You only need to say high temperature. If you're given a number, you should be given a number above 320. And to be honest, if you gave below that, you might have got the mark here anyway if I wasn't paying full attention to it. The second mark where people aren't getting it are for saying steam or a catalyst. We mainly focused on catalytic cracking in class, but at least a few of you are looking in your revision guides and noticing that you can do steam cracking as well. You can name the catalyst, and if I've not given you a mark for this one, if you said an iron catalyst and I've marked it wrong, do you know what? Like maybe I should give you that mark. So have a look and see if I already owe you an extra mark on the first question. On 1.6. So on this one, a lot of people are getting the marks the same because the new products made by cracking are more useful or they're better fuels or anything like that. Not many people talking about polymers, but there's very, very few people talking about meeting the greater demand. So the idea behind this is that the longer chain hydrocarbons are more plentiful and not required for as many uses like roads and roofs and things like that. So they can be broken down into smaller, more useful, more volatile things that are used as fuels, which there's a bigger demand for. So it's a case of supply and demand. So that second mark, that's where most people are missing it, and that's nationally the same sort of picture as well. Most people nationally were losing a mark there. This last bit about making sure the carbons and hydrogens add up to the right numbers, that's your classic one for this, and most people were getting that right, so well done. So it's C15, H12 there, so there's 3 carbons missing. There's 32 there, there's 26 there. That means there's 6 hydrogens missing. Okay, well done on question 1. Right, let's have a look at question 2. There were some interesting parts to this. The good answers were obviously absolutely perfect. There was some confusion about some of these tests, so let's jump straight in and have a look at it. When we're marking a 6-mark question, there's 3 levels. Okay, when I'm looking at it, first level is where you're not really getting a very clear outcome. So if you've got 1 or 2 marks on this, you've used some of the things in the question, but you're not getting the right answers. So like you're getting the wrong results or something like that. Level 2, then you got most of the key points. If someone picks up your idea, it's not really going to work. They're not going to be getting the right ideas. You've missed stuff out, or you've got some of the wrong information in there. And obviously, level 3, this is where you've got nearly everything, and just have a little look for the bits that you're missing. So, Let's look at the lithium first of all. That's in the thing, just because it says lithium ions first. So any of the metals we're looking at doing a flame test for, or a sodium hydroxide precipitate. In this case, then it's going to be the flame test. So some people just were saying like just put the tablet on the wire and hold that in the flame. It's always a solution that we're looking at doing. So crush it, dissolve it in some water. You could even get away with putting it in the acid that was mentioned in the question, like some people said. You're going to need a clean wire. One of the ways you can do that is dip it in the acid. That's why they've mentioned the acid there. You're then going to put your solution, your loop, your metal into the solution, and then hold it into the roaring blue flame. And then you're going to look at the color. If it's lithium, it should be crimson. Okay, you can get away with red, but then that can get confused with some of the other ions. So crimson is your textbook revision guide perfect answer. New paragraph, second section. Let's start talking about the carbonate. The most incorrect answers were pretty much just saying put your carbonate in the pill into the lime water, and if it goes cloudy, you've got a carbonate. I mean, well done for knowing that it's going to go cloudy with the lime water, but you've missed out all the key steps there. So you're looking at adding the acid. The acid is going to react with the carbonate and give off carbon dioxide, and then you need a way of transferring that. So a lot of people remember doing this in class. The way I did it was we sucked up with an invisible gas some of the carbon dioxide and then put it into the other tube, and then it just started to turn it cloudy. Textbook revision sort of things will use a delivery tube, a little tube going from your tube into a test tube with lime water, and it'll bubble through that and it'll turn it cloudy. Okay. Second part of the question, 2.2. So mixtures with a particular ratio of things like paint or drugs or things like that, that's a formulation. It's just one specific little keyword I can remember doing the lesson with a chunk of you. And it's one of those that if you're not looking at your revision guide, don't know why you're learning it, it's just one of those marks you're going to lose. And I think nationally there's something about 80% of people got that wrong. On 2.3, this question was worked out pretty well. Most people getting 58.3 for the full 3 marks. So it's saying we've got 1.2 grams contains 700 milligrams of lithium carbonate. The obvious problem there, first of all, is that you've got milligrams and grams, so you'd want to convert them together. So you could say that 1.2 grams is 1,200 milligrams, or you could do the reverse. And then because you've got like and like units, you can then do a percentage. So it'd either be 700 out of 1,200, or 0.7 out of 1.2, and then times by 100 to get to a percentage. And the answer then should be 58.3%. Okay. 2 done. Onwards to question 3 then. Well, look what we've got. So, yeah, just like the national picture, most people got this first mark. Not a state. So there's 3 states that you're learning about at GCSE at least. Are solids, liquids, and gases. So the AQ, with or without the brackets, or even writing the word aqueous, would have gotten you the mark there. For 3.2, most people getting 1 mark. Let's have a look at what the issue is. The first mark is for saying something that you could use to measure the change. So that could be a measuring cylinder, an inverted measuring cylinder, a burette, again filled with water, inverted over a trough, a gas syringe, slightly easier. A balance you could have so that you could measure the mass change, or any of those is just the first mark. Okay. It's asking how you could calculate the rate, so that is going to be a unit per second or per minute or something like that. So you need something to time it as well. So the second mark that a lot of people missed is a stop clock, timer, watch, anything like that. Okay, lots of people got the time bit wrong. Most people gave like a measuring cylinder and a burette, or some people couldn't remember the name of it, so they tried drawing it, which was kind of cute. Well done to you. All right, this one, most people got the full 3 marks. It's quite easy graph plotting skills. It's not too challenging for the sort of kids that we're looking at with you guys. And the same picture nationally on this as well. The graph skills are pretty good. And if you're ever going to lose marks on this, it's just because you're not within one little square of where you should be. Okay. Looking at the data from the table, you've got to be a little bit careful on this one. No, very few people were getting 3 out of 3 on this. Okay. Now, I was a bit generous on this. There was some people getting credit for saying the first 10 seconds were the fastest. Well, if we're being a little bit technical, if you look at the table, you don't know what happened in the first 10 seconds. It starts at 10 and then goes to 20, so you don't actually know. We presume it is, but there's no data for that. So really, that's not where we should be giving credit. So the three things that we're looking at relate to the fact that this is a curved graph that is starting high and going lower. So the rate starts fast and it slows down, okay? The rate is decreasing. That's our first point. Okay, the second point that most people got, if they were getting any marks for this, is that by the time it's got to 60 seconds, there is no reaction happening, as evidenced here in the table when it says there's no gas being produced in centimeters cubed per second. The one that everyone's missing then is this fact that the rate is changing over time because it's a curve, okay? So I think I was allowing it for some people who were saying that the rate change was not proportional. The rate is happening, the rate of change is decreasing. It's more slow as the time is increasing, okay? Number 3.5. Yeah, most people were getting this one right as well. So if we're looking at variables that, so which statements are correct? Yeah. So more bubbles are being produced in the first 10 seconds. That's because it's fast at the start, isn't it? And the magnesium is being used up more quickly in this case because we're using a higher temperature. That means the rate of reaction is going to go faster. The activation energy is going to be the same regardless because it's the same type of reaction. It's the same actual reactants that are occurring. And the reaction finish at the same time isn't going to be true because it's going to be faster because it's going, higher temperature, more collisions. Total volume of gas is not going to be greater because there's the same amount of reactants that are going into it. So there's a fixed amount of products. You could do a reacting masses thing and you could actually work out what the maximum yield is. All right, short waffling, Dawson. Okay, get ready to kick yourself a little bit for this one. Let's have a look at question 4. Please don't kick off if you got no marks here, but some people just sort of said, tube 1, rust, tube 2, no rust, tube 3, no rust. You get the idea. Okay, the question is to explain what would happen, and it's worth 5 marks. So it's not just tick an outcome, okay? So, test tube 1, let's have a little look at the picture. There's an iron nail and there's water, so we need to be saying that, and it's exposed to the air. There's no lid or anything in it. So we need to say that the iron nail in test tube 1 is going to rust because it is exposed to water and air, and obviously air contains oxygen. Okay. For test tube 2, we need to say that it's not going to rust. The reason it's not going to rust is we've got dry air, so that's had something like some silica or something in it to remove the moisture. We're not allowing any more air in, whereas oxygen can get to it, water can't. Okay. So test tube 2, no rust, no water. Test tube 3, when you boil the water, it actually stops the gases being as soluble, so the water can escape from it. So the oxygen can escape from it, and there's oil on the top to stop the oxygen getting into it. So the oil is a big clue that you're not getting any oxygen in it. So again, quick one, test tube 3, no rust, no oxygen. Test tube 4, this one's been painted. Quite commonly people are saying it's going to rust or the paint's going to fall off or stuff like that. The paint is there to protect it. That is why people paint it. And if you might, yeah, but it's going to happen anyway. You need to repaint it eventually. Read the instructions. It says it's there for a week. All right. You don't need to paint a car every week, do you? The paint stays on it for a good amount of time unless it gets damaged. So test tube 4, no rust because the paint is forming a barrier to stop oxygen and water getting into it or something like that. Test tube 5, stainless steel doesn't rust. Nice sentence like that would have been good. Okay, because it's alloyed with chromium and nickel, it doesn't rust anymore. Okay, some people were putting that steel doesn't rust only things with iron rust. Steel is an alloy of iron, so nice try, but no. 4.2 then. Why is the magnesium on the steel ships? First of all, if you just say that this is sacrificial protection, you can have the mark. But if you didn't use that terminology, then you can explain what's going on. So what's happening there is that you've got the magnesium is more reactive. Okay, so for nice 2 marks, it's sacrificial protection because the magnesium is more reactive. If you didn't say sacrificial protection, you could have said that the magnesium is going to react instead of the steel or the iron from the ship. 4.3, quite a lot of people not looking in the revision guides and looking at this section about the using the chemistry. And this is highlighting one of the issues. Okay, aluminium in the wind frames is not painted, oiled, or anything else. It's not got any special coatings or something like that. Literally, it's that the aluminium oxidizes and forms aluminium oxide, first mark, and that is then a barrier which stops any further reactions. It stops any more oxygen getting into it. So if you scraped that layer of aluminium oxide off, it would form a new coating and it would stop that getting through. So if you look at the window frames in school, they're metal, they're not painted, that's the aluminium, and it's dull because it's got a coating of aluminium oxide on it. Okay? Right, question 5. Get your thinking head on in a second. So, first one, a lot of people got 1 out of 2. The most obvious thing is by saying that either wood is renewable or it's you can plant more of it if you're being a bit more simple, or the opposite, you can say that natural gas is finite or non-renewable. You don't get 2 marks for saying one and then saying the opposite. Okay, so only you may have ever make the 1 point and don't repeat the opposite. The second point then, because wood uses photosynthesis to take in carbon dioxide and then burning it gives out carbon dioxide, you could say something along the lines it's carbon neutral, or even if it's not carbon neutral, it's on the way to being carbon neutral. Okay, so it has a smaller effect on the greenhouse effect. Have a little look if I've been a bit harsh there, because maybe if you wrote it doesn't produce as many greenhouse gases. I might need to look at renewing that. Let's have a look at the mark scheme. Oh, I know why I'm being mean there. It produces the same amount of greenhouse gases potentially, but it doesn't cause an increase in the overall atmospheric amount of carbon dioxide. I hope that makes sense and I don't have to deal with 30 questions about that. 5.2, carbon monoxide then, the main thing that I'm looking for is that you're saying incomplete combustion and explaining that there is not enough oxygen for that to happen then, okay? More people were saying that about not enough oxygen and very few people actually getting both marks and saying incomplete combustion. And if I have a quick look there, I think that was about half students nationally got both marks, and if they were missing out on marks, it's the incomplete combustion bit. A nice balancing equation here. Just look at the answer here. It's 2, 3, 2, 4. And if you need me to go through that with you in class, it's fine. Balancing equations is something that you need to get used to, and it'll come up year after year after year in both papers. And this is why we need our thinking hat on next. Right. So, most incorrect answers, you just basically took one number away from the other and had a little bit of a stab at it. I can get that. If you did that, just remember, right, these volumes up here are in dm3, in decimeters cubed, in litres, and this one's in centimeters cubed. So even if you've got an absolutely naff answer, don't forget to change it to convert it from decimeters cubed from litres into centimeters cubed, millilitres. All right, so 7.25 decimeters or 7.25 litres would be 7,250 centimeters cubed or millilitres. Okay, you can pick up a mark for that even if you've got no understanding of the rest of the stuff we're going on for. Okay. Right, so we've got 3.6 decimeters cubed of carbon dioxide produced. Okay, we're not going to have needed to use up all of the oxygen being produced. Let's have a little look at the ratio. There's 5 oxygens to 3 carbon dioxides. Okay, so if you're looking over here, we first of all get your mark for identifying that it's a 5:3 ratio. What we basically need to then do is get your carbon dioxide, 3.6, divide it by the 3 from the ratio, and then times it by 5, which is then going to give you how much oxygen you would need to produce 3.6 decimeters cubed or 3.6 litres. So that's this step here. You'd need 6 litres, you'd need 6 decimeters cubed. How many did you have in the first place? 7.25, so find the difference. That's a difference of 1.25 decimeters cubed. Here's your conversion. So you're either timesing or dividing by 1,000. Remember when you're doing this, it's timesing by 1,000 to go from 1.25 litres or decimeters cubed to 1,250 centimeters cubed or millilitres. Okay. You could do it the moles way, where there's an alternative method here, where you could do use the MR from the carbons and the oxygens and work out a number of moles with the same sort of ratio, and you get the same answer. But I don't remember anyone actually doing that. Okay. Right, question number 6. A lot of the stuff in here is not hugely technical, but it focuses on a bit of the revision guide that I think people are overlooking and neglecting in terms of the revision. The good news is it's probably not going to have the same things on next year's test, but there's areas in this topic which are coming up and you've not done well, and that could also mean that different areas of the same topic might come up next year, and you also don't do well. So previously, we were talking about formulation, and one of the previous questions, that's in the same topic as well, and it's one of the ones where people are just showing they don't know some of the facts. So this is where we review polymers in topic 2. It links into the paper 1 materials too. There's the polymer, so we need to make it back to the monomer. First thing is then if you can have a monomer, you can have your carbon-carbon double bond. So in between the 2 carbons here, we need to put a double bond, so the 2 lines that make it look like an equals. The final things then would be to put the lines above and below. So a line up to the hydrogen, a line down to the hydrogen, a line up to the carbon, a line down to the hydrogen. So there should be 4 little sticks coming off each of those. What you don't want to do is extend any lines out to the side, because that's going to cost you marks. Okay. At this point, it's just I told it's like dinner ladies, and they've got their arms crossed, and then which is what's this picture down here is going to be. And then when they start forming those big long chains that you get sometimes in primary schools, they're going to open up their arms, break that double bond, and extend it either side. On 6.2, looks a bit scary because it's got C's and H's and O's and monomers and all. Okay, but functional group on monomer B, you've got that COOH, that cool. That's your sign for a carboxylic acid. A carboxyl is in the allow, even though that's actually the proper term for that group. But it shows you that it's a carboxylic acid. For 6.3, you might remember in the lesson that I showed you polysaccharides and monosaccharides, and when you join them together, it's a condensation polymerization. We talked about nucleotides joining together to make DNA, and that was a condensation polymerization. And we had peptides, that was amino acids joining together to make proteins, polypeptides, and that was a condensation polymerization. And this was another one of them, and all those condensation polymerization reactions produced water. Okay, the other polymerization reaction, the addition polymerization, for things like ethene making polyethene, you just got the 2 monomers and joined them together. There was nothing else produced as well. So it's either 100% atom economy joining things together, or if it's got another molecule being produced, it's water. Okay, I don't think our kids, our year group, did as good nationally there, because I think most kids nationally were getting over like 50-60% of people getting that right. 6.4 is another one highlighting why you need to look at this section for the revision. Get yourself on Seneca, go through the area, like just make sure you're familiar with the key terms for it. Okay, picture the lesson, why is my pen a dinosaur? And then the several times we've seen it, we've looked at 2 different chains of molecules. One of them is joined together by little crosslinks, and the other one has just got some weak forces. So if it's joined with crosslinks, it's got stronger forces holding things together. So it's got a high melting and boiling point. So it's a plastic like your kettle. When it gets hot, it is not melting. Okay. This one's asking about one that melts. So this is kind of like a crisp packet. If you ever put that crisp packet in a microwave or in an oven, then it will melt down to a much smaller, harder size. It will change shape because it's gotten hot. That sort of plastic is called a thermoplastic or a thermo-softening plastic, and hopefully that sort of makes sense why it's called that. It's a good name for it. Okay. The reason it's a thermo-softening or a thermoplastic is because it doesn't have crosslinks. Okay, so a common example, a natro-thermoplastic, is a rubber. So just like your synthetic rubber that you use to rub out pencil, natural rubber that comes out of a rubber plant, you can rub along on the surface and it'll flake off. Okay, it's not very good for tires because your tires fall apart. You do a process called vulcanization and it forms crosslinks, and then you get to the sort of rubber that you have on bike tires and car tires, where it is much, much stronger because it's got those crosslinks. Okay. So if you didn't mention crosslinks, most of the people that were getting marks for this were saying allowing weak intermolecular forces, but what you couldn't say is that it's weak bonds, because bonds are between the atoms and they're actually really strong in something like this. And you couldn't say that it's weak forces in between the monomers, because the monomers are actually held together by, into a polymer chain by, again, those strong bonds that I was talking about a minute ago. Okay, this is definitely part of the topic to look at for revising, because the stuff in this chunk was a little bit weaker overall. Composites is another good example. Glass fibers were the one that people most likely got right on this. They are the reinforcement. The polyester is the matrix. So when you have a composite, you've got the main strength item, which is held together by some sort of a glue or resin. So In carbon fiber, for example, there's the carbon fiber sheets, and then there is a polymer glue that sort of holds them together. Okay, so knowing that matrix and reinforcement was simply just two revision guide, take home, I've revised this and done flashcards on it, sort of bit of knowledge. 6.6, people were struggling to get the right sort of words into this. Okay, it's dead common that people were saying that it was it was going to protect them from water, so it's going to make it waterproof, stop it reacting with water or something like that. It was also quite common to say it was stronger, and they are proper comparative statements. Like stronger implies that it has more strength than it previously did. Really weak answers were things that were saying things like it will make it last longer, but you've not really said why it's going to last longer. I mean, it could last longer if you just put it in a box and don't use it, but that doesn't really answer the question. So that's why you might not have the mark. Okay, question 6 done. Right, let's have a look at number 7. Right, people either seem to know this, or maybe fluff a little bit of response. And if you've fluffed a bit of response, I think I've been a bit nice on some of the marking here, and I think I should probably take some marks off you, but oh well. Right, aluminium, this is the one when you look at sodium hydroxide precipitates, this is one of the ones that they like to ask you. Because you've got that beautiful blue colour there for copper, and that might be a nice question for a foundation paper. But for higher tier students, they like to ask you about aluminium because it does the whole white precipitate and then it redissolves in excess. Or they like to ask you about iron because you've got the green and the red or the orangey rusty colour to get confused over between the iron 2 and the iron 3. So 7.1, what's the test? The bit where I've been nice is if you got the test wrong, then you couldn't get the results, the marks for the results. But I think I did actually mark it right for some of you. Oops. So the test is adding sodium hydroxide. Some of the incorrect answers are some of the other reagents that you'd use, like silver nitrate or something like that. The result, you'd see a white precipitate first of all for your first mark, and then you should get the white precipitate redissolving when you add excess or as you add more sodium hydroxide. Okay. 7.2 again, one of these tests. Testing for sulfates then, most incorrect answers that made sense when you put in the tests. Again, you were going down the silver nitrate route, but that's the one that you use for chlorides. Okay, so barium chloride or barium nitrate solution, either one would be fine depending which one you've picked up and learnt. You also need the acid there too. Nitric acid or hydrochloric acid are fine. You can't say sulfuric acid because that might make some sulfates that contaminate your test. Okay, the result then would be a white precipitate. Again, if you just said white precipitate and you got the first one wrong, then you should have this second mark wrong, and maybe I was too nice and gave you a mark. Oh well. 7.3. Let's have a look. This was all right. This this is actually an RPA, and and you know what? I think year 7s could quite often come up with something close to this if you gave them a lesson to do it. You don't have a lesson, you only have 5 minutes. Don't feel bad if you lost some marks. But the main thing that we're looking at is being able to provide a way that you can remove the mass of the water in the basin and find out the solids. So if you know the mass of the basin, first of all, and then you add the full 100 centimeters cubed of the sample, heat it up, evaporate the water. Maybe, some people said leaving it to crystallize after a bit so that you're not going to have spit spitting over the side. Very nice, not losing any mass. And then reweigh it. You can find the difference between the two. So from the original basin to the basin with the salt. One of the nice things to look in about getting consistent results is that you would keep heating it and keep heating it, or keep leaving it out until you get a constant mass. And that constant mass is going to be because no more water is getting lost. You could have a small amount of water in a sample that looks visibly dry. If you're also looking at improving the quality of your answer as well, repeating it or calculating a mean, or if you only did like a 10 centimeter cubed sample, then multiplying that up to the 100 centimeter cubed, that'd make sense too. Okay. Okay, let's look at question 8. Story time. I'm going to read you out from the examiner's feedback here. and this applies to a lot of us. Answers that scored no marks at all tended to be entirely about how the atmosphere on Earth is thought to have changed. If your answer is about question Earth, is about question Earth. No. If your answer is about Earth, you're not answering the question. Okay? The question is about Titan. So let's have a look at what we should be saying then. So Titan's mainly nitrogen with a bit of methane and a very small amount of other gases. First thing then, there is no oxygen, or is there very, very little oxygen? Okay, there's your first bit of credit. Second thing then that you need to be saying is that you're assuming then that photosynthesis has not occurred or there's no plants because plants would be producing oxygen. That's one of the ways that we can be looking for life on another planet without actually being able to see it the way it's standing there waving, is for looking for the signs of the life. And if there's got photosynthesis producing oxygen, then that there's an oxygen in the atmosphere. You could see that through spectroscopy. Might be worth sending a probe there, have a little look, see if we found some life. Anyway, back to the question here. So first mark, very little oxygen. Second mark, so probably no photosynthesis. Third mark, there's very little carbon dioxide there, if any at all. And again, link that back in. You probably, if you've not got carbon dioxide, you're probably not having photosynthesis happen either. Okay, most of the incorrect answers then, you're talking about Earth's early atmosphere. It's good that you know about that. That might come up next year. 8.2. Right, I hope you're still listening to me here because this is chuffing important. The reason it's worth listening to me waffle on with this stuff rather than just putting some music on and just looking at the mark scheme is these little technical bits. So a lot of people have the idea about methane forming a barrier that traps heat in, but maybe only got one mark. So when the incident radiation from the sun, and again, we need to be talking about radiation or even ultraviolet or infrared, I think, is incident when it's coming in. Because it's shortwave, it can pass through this layer of gases, the methane or something like that. As the sun likes to do, it hits the surface then for the second mark, and it gets re-emitted as heat. Okay, just so if you're in a police helicopter and you're watching your chase, you can see the heat being radiated off the ground where it's hot from the sun. Okay, the radiated stuff is a longer wavelength. The heat, the infrared, has got this sounds like physics, doesn't it? It's got a longer wavelength than the shorter wave ultraviolet light we said about going in. So this longer wave stuff is trapped by the methane in the atmosphere, whereas it wasn't before. Most people then got this. If no other mark is awarded, allow 1 mark for methane absorbs long wavelength or radiation, or methane absorbs infrared radiation. Okay, but if you weren't talking about infrared, if you were just talking about light in general, yeah, you might have got the mark, but if you did, it was skin of your teeth. Okay, teeth don't have much skin, by the way, in case you're wondering. 8.3. The atmosphere of Titan contains a small amount of propene. It's unsaturated, give the test. A lot of the answers here, the people were saying about it being a really smoky flame. Now I remember showing that at one point, but I also remember saying at the same time that that's not a conclusive test for it because there's plenty of stuff that burns with a smoky flame that's not an alkene. So we start with bromine water, which is sort of like that browny orange color. If it's showing that it's an alkene, propene, then it will decolorize, and notice that it's saying from brown to colorless. Ignore clear. Okay, you can't say clear. Drinks bottles like my amazingly reddish / pink, depending on how you look at it, bottle is clear, but it is not colorless. Okay, so you got to be really clear in what you're saying there. We are getting there. Sorry to bore you. Question 9 then. I mean, this is a nice one. Test for oxygen. It's a glowing splint or a glowing spill or whatever you want to call the little stick, and it will relight. We don't want to hear you saying about a pop, and quite common wrong answers say things like a burnt splint or a lit splint, and they're not right. You should only really get both marks or the second mark if you got the first mark right. So if you said a lit spill, which relights, I might have been stupid enough to give you one of the marks out of the two, but I really shouldn't have, so please bear that in mind. 9.2, we're looking at 2 improvements which could make the result valid. Okay, so let's just go to this keyword validity. I do hope you're familiar with things like the difference between reproducible and repeatable. So reproducible is where someone else can reproduce your work, whereas repeatable is that you can do it again. That's not this question, but I'm just highlighting that these are some of the words that you need to know for these like little how science works questions. This one, it's about validity. So something is valid if it helps you to answer the hypothesis or the question that you're investigating. Okay. So if you, for example, you measured the increase in the mass of the conical flask and the contents, that doesn't help you answer the question about the particle size and its effects of the rate of the reaction. Okay. So the answers that we're looking for is place the conical flask in a water bath at a constant temperature. The reason then that you'd be looking at doing that is because temperature can affect the rate of reaction because it can affect the speeds of the particles and then how likely they are to collide and you get the picture, collision theory. Okay. The other one is to use a mass of 1 gram of manganese dioxide each time because up here it just says a spatula. So if you're saying 1 gram, you are making it a better control variable that you are making it test. Control variable is the better way to say it. Okay. Oh, no, you can remind me later. Thank you. 9.3. More side, you're good at doing graph stuff. Okay. And at least if you weren't, you're pretty good at just getting to two significant figures anyway. So it says determine the mean rate. So although it's got a curve on there, you didn't have to do a tangent on this one. Yay! So the mean rate of reaction between 2 and 4 minutes. Okay, so 2 minutes. If you go up from here, and we're doing it for which line are we doing it for? Course 1. So we go up until we hit the course line. There we go, and that is that one 45. And the 4 minutes, that's going up until it's at 56. So 45 to 56, that's 11 centimeters cubed. Okay. How long's that happened in? Well, that's in 2 to 4 minutes. So that's 2 minutes. So some people, you lost a mark because this answer here, it should be in centimeters cubed per second, and you left it in minutes. Okay. So for example, if you did 11 centimeters in 2 minutes, you divided 11 by 2 and you got 5.5. That's where you lost your mark. Okay. If you turned it into 120 seconds, you did 11 centimeters cubed in 120 seconds. That's this calculation here. That's where you get this funky number, 0.09167. Two significant figures, and it's 0.092. Yay. Right, 9.4, cheeky one. Let's just point you a bit of information and show you what the curve would look like on the graph if you watch where my mouse goes. So this says student B is doing the same experiment with coarse lumps, okay? But they're using a 0.2 molar compared to a 0.3 molar, okay? So there is less concentration. So on the graph, if you got a mark right, most people just did a lower curve that went somewhere below the course line, but then met at the top, 1 mark out of 2, because it would have a slower rate of reaction because it's got a lower concentration. A lower concentration means the particles are less likely to collide into each other, therefore less likely to have a reaction. The rate of reaction is slower. You actually then have like 2 out of 3. You have like 0.2 instead of 0.3. So you've actually got 2/3 of the stuff that you would have had originally. So you can make only 2/3 of the total gas that you would have made originally. Nicely, it started at 60 and 2/3 of that is 40. So your line should curve up and then level off at 40. Okay, at a slower initial rate. There's only about 1 in 20 people in the country got both those marks there. So if you did that, and there was quite a few of us that did that, very clever indeed. Good work. All right. 9.5. The rate of reaction for a fine powder rather than a coarse. Wow, some of you just got this backwards. Okay, and this comes back to talk about rate of reaction a lot, haven't we? Here. So if you're getting it right, a fine powder has got a larger surface area. Okay. If we just flat out said that wrong, this just said it the opposite way around. Naughty. Okay. So the second mark is then saying because it's got a larger surface area, you're more likely to have collisions, which means it's going to be a faster rate of reaction. Quite a few people started talking about the kinetic energy of the particles, which is the speed of the particles. that can happen for temperature, but that's not going to happen for concentration. Hopefully you follow that one. Okay. Oh, look, it's the last question. Well done. Oh, look, we're given some ARs, and we're going to have to add some of them together at some point, aren't we? So remember, if you don't know what you're doing on that, add some of them up. It's a decent start. We're doing an atom economy. If you did this wrong, it's probably because you added all the stuff up on the left and all the stuff up on the right, and they both equal the same amount. So he's like, oh, it's 100% because like I've got this much on the left and this much on the right, and that's the same number. Right, atom economy, like anything when you're doing an efficiency and economy, is the what good stuff you got out of the total amount of stuff. Okay, so in physics for energy, it's the useful energy over the total energy. So in this case here, we are producing carbon monoxide. Okay, that is, stupid Dawson. We're producing hydrogen. Okay, that's going to get used in the Haber process, like our number one, like most amazing reaction that we love in the world ever. You're going to miss that when your GCSEs are done, unless you do chemistry A level. So in this process, we're getting 3 hydrogen molecules, and we're wasting all these carbon monoxides. So we need to get each hydrogen molecule. Hydrogen is 1, and H2 then it weighs 2. And then there's 3 lots of 2 because it's got a big 3 in front of it. It's 3 lots of 2 is 6. Okay, that is 6 out of everything that went in. So this carbon here, these hydrogens, and these oxygens all added together should be 34. So you got 6 useful stuff here out of the 34 in total that you put in. Times it by 100 and you get 17.6%. Okay, should be quite a nice easy question just as long as you're familiar with what an atom economy is. Vision guide. 10.2. Right, when it's talking about pressure and equilibrium, you know we're talking about Le Chatelier. Okay, so why are we using low pressure? Pressure is about the number of moles of stuff. So let's count it up here. I've got CH4, there's no number in front of it, so there's 1 of it. And I've got H2, there's no number in front of it, so I've got 1 of it. So all these together here, I've got 2 on this side. On this side, I've got CO, there's no number in front of it, so I've got 1 of it. And I've got 3 H2. That 1 and 3 here is 4 together. So I've got 2 and I've got 4. So if I increase the pressure, I'd move away from the products and I'd go back here. So increasing the pressure in this case is bad. So it says, why do we use a low pressure? So a low pressure is going to help shift the equilibrium or favor the forward reaction. So that's this first bit here. We're getting a higher yield or more hydrogen or more carbon dioxide or more product or whatever. Favors the forward reaction. Loads of different things you can have there on the mark scheme. And the second part that you're looking at having on it is the reason why. It's because there's fewer moles. I know you don't like the word moles, so there's fewer particles. Anything which is getting that concept across. Okay, it does not allow you to say fewer atoms because it's not actually counting how many atoms make up that molecule. It's about how many of those molecules themselves there are. On 10.3, cheeky question. All right, so we've said on Le Chatelier's, if you increase the temperature, it tries to reduce the temperature. If you increase the pressure, it tries to take it down to the side with the least amount of gas. If you use a catalyst, it will increase both the forward and backwards reaction. Here's the cheeky one. All right, I've got 1 there and I've got 1 there, so there's 1 on the there's 2 on the left-hand side. I've got 1 molecule there and I've got 1 molecule there, so there's 2 on the right-hand side. If I increase the pressure, which side has got the least number of moles of gas on it? They're both the same. There's no effect. Oh, naughty. Quite a few of you spotted that. Proud of that. You did good. Very clever indeed. This Haber process, the Haber compromise, definitely something that we've done like in class and is in revision guides. And your favourite YouTube celebrity person, Sean, he talks about stuff like this. So make sure you go over it. Right, how many times greater the percentage yield of ammonia obtained would be between, here we are, let's have a look at these. First one is 450 degrees Celsius, so that's this line here, the bottom line, at 200 atmospheres of pressure. So there you go up from 200, oops, clicking Dawson, up from there, and we're 1 little box underneath, so halfway between 20 and 40 would be 30, and then a box underneath that would be 28 because there's 5 boxes, so let's split the 10 up into 2s. Alright, so we've got 28 for the first one, which is better than Clyde did when he did when he did this with his little animation thing on this. If you weren't in Clyde's class, you don't know what I'm talking about. And then 350 degrees, that's this top line at 285. So there's 250, 60, 70, 80, 5 there, and we're going up, and we're going across, and that's like 63 because it's halfway in between the two boxes. So it's gone from 28 to 63. How many times bigger has it got? So we want to see how many times does 28 fit into 63. So the first little waffly bit when I'm talking about Clyde, that's where we're getting these numbers, and that's where you're getting your first mark. If you can see the lines drawn on the graph, it's really good for the examiner because you can see what you're doing and where you're getting those from, and it helps tell the story about what you're doing. Okay, this next question is a bit of the question where the second mark, you're seeing how many times 28 fits into 63. If you got the first bit wrong, then you can still get the marks for this bit, as long as you're using your you're doing the correct thing from your incorrect values. And if you got the right numbers, your answer should be that it's 2.25 times greater, or 2.25 times greater. Okay. Yeah, a little bit tricky that. Number 10.5. Middling performance on these last ones. A pressure of 285 atmospheres of pressure is not used. Why? This one was all right. A lot of people are saying that either it's going to be expensive to try and maintain that or create the equipment to hold that, or if you don't, there's a risk of the explosion. For 10.6, just need to have a look at the graph here. So how does it show it's exothermic? Well, if you go from 350 to 400 to 450, the percentage of ammonia is decreasing. That's telling me that if I'm increasing the temperature, it's going to, Le Chatelier, do the opposite. It's going to favour the endothermic to help reduce that temperature. So therefore, the forward reaction must be the exothermic side. I know some people just went cross-eyed listening to that. 10.7, right. A lot of wrong answers here talked about ammonia being used to make fuel for cars. You don't burn ammonia. All right, ammonia is with another section that could be really nasty if you started asking you about fertilizers. All right, look at that bit. So ammonia can be used to make ammonium nitrate, which is great for your nitrogen, which is used for plants. Go look at your biology stuff at what nitrogen does in plants. It can be used to make other salts like the ammonium phosphate if you react it with phosphoric acid from phosphate rocks, and that's part of your NPK fertilizers. Okay, so let's have a look. First thing, it's used for fertilizer, and the demand has increased for fertilizer. A lot of people got the reason why we need more fertilizer or something like that is because the world population has increased. Boosh, that's your final mark. Okay. Feel free to ask for any help that you need or anything like that. Good luck in your final exams, guys. Proud of what you've done so far.